Hello, welcome to the Habsbot presentation for the P3 Student Design Competition. My name is Luke Aldana, and other presenters will be Shub Koradaya, Blake Valera, and Kate Boyd. We are a collection of 9 engineering students from Colorado State University, Walter Scott Jr. College of Engineering. So what are HABs? Harmful algal blooms are colonies of algae that lower the natural oxygen levels in the water, and they also produce life-threatening toxins to humans and other animals. Why are HABs a problem? They have huge negative health impacts on humans and other animals that might be swimming or drinking out of the water. This also interferes with economic activities like recreational swimming, fishing, and water treatment. What is the intended functionality of the Habsbot? It'll be completely autonomous. It'll have various sensors for continuous monitoring for algal blooms, and it'll have the ability for sample collection for further toxicity testing using micropads. It'll be completely sustainable using solar power, and its main function will be a rapid, reliable HAB detection. For the power of the Habsbot, we have all the electrical components broken down into a list here. We have the Raspberry Pi for data processing, a couple sensors for obstacle avoidance, and so on. We calculated that all of these components will be less than 100 watts per hour. So we figured a 100-watt solar panel will be plenty enough to power this load. For the navigation of the Habsbot, there's a little flow chart here. Basically, the user will provide a screenshot from Google Images with its coordinates of the body of water. They'll input it to a program. The machine learning will trace it out and assign the coordinates. And a GPS will constantly get the current location of the Habsbot. And a PID control system will check the error between the GPS coordinates and the machine learning coordinates, and it'll adjust its path depending on that error.
The Habsbot will monitor the algal bloom through the concentrations of chlorophyll A and phycocyanin. It will be done so through the fluorescence detecting sensors attached to it. After detecting the algal blooms in the water, they'll be tested for concentrations of microcystin and cylindrospermopsin. They'll be tested through micro-PAD testing, which will be read by a potentiostat. The data obtained will be referred to the EPA guidelines for further toxicity determination.
The size of our drone ended up being determined by the size of solar panel that we used. The final dimensions are roughly 5 feet by 4 feet by 3 feet. We selected carbon fiber as the material to decrease the drone's weight while maintaining its strength and water resistance. And some notable design features include a self-balancing center of mass, a NEMA 17 stepper motor rotates a T200 thruster to provide the drone with propulsion and steering, and LiDAR and sonar allow the drone to avoid obstacles.
Overall, we aim to have our Habsbot prowling the waters autonomously, powered by solar and continuously reading chlorophyll and phycocyanin concentrations as it goes. This robot will be able to distinguish between normal algal blooms and harmful ones, and will even be able to tell you the type and concentration of toxin in your water, so you'll be one step quicker in addressing the bloom. Whether it's wastewater, a reservoir, or your local dog park, the Habsbot can contribute to the health and safety of lakegoers, plants, and animals alike. Next steps in this project are to begin construction of our boat's components and to piece together a prototype. Thank you all for listening.